We one second. So we're gonna start where we left off. We did cover, I guess, most of the stuff related to AS. Okay, and we did homogeneous catalyst. We did heterogeneous catalyst where I talked about we did examples of catalysts. I told you about adsorption and deadsorption. Or this is actually in the recent marking schemes, it's written as desorption. So I guess we're gonna use the latest one. And we talked about the homogeneous catalyst, and yeah, we were talking about the homogeneous catalyst, right? So we're gonna start there. Now, so homogeneous catalyst was that the catalyst and reactants they were in the same phase, which means that they had the same state. One of the examples was your one second, let me add people. So one of the examples was this one, the acid rain formation. That was an example of a homogeneous catalyst. The other example that we were doing was related to electrochemistry, which was that you had these reactions, S2O8 reacting with I minus one. The first one had a higher potential, so higher potential wanted to gain electrons, so it gained electrons. The lower potential was the one that wanted to lose electrons, so it lost electrons. And you got this equation. I added up the reactants and I added up the products and I got this equation. The E naught cell was a reduction potential minus oxidation potential. So that was 1.47 volts, which was highly feasible, very, very feasible. It was a very high voltage. But the reaction had very high activation energy. Why? Because both ions in the reaction were negative ions, and therefore they were not going to meet each other. They were going to repel each other, so they will not interact, and therefore there would be no reaction. So like charges repel, which is why it would be almost impossible for them to react. So what you do is that you add iron ions as catalyst. You can remember this particular example, it has to be memorized. So what you do is you add iron ions as catalyst. And what that catalyst does is, so Fe3 plus or Fe2 plus, they both or a mixture of both or both of them. They're going to be used as a catalyst, and you'll be asked about what role do they play when they react as catalyst. So these two electrodes are not going to react with each other. So I'm going to separate them. They are absolutely not going to react because both of them, it turns out they are negative ions. So the next thing that happens is that you've got iron ions. So I'm going to write down the electrode for iron ions, which is this one. It's Fe3 plus. It gains one electron and it's in equilibrium. Could go forward or backward with Fe2 plus. Just so that the electrons are equal, I'm going to multiply this equation by two because everyone is losing or gaining two electrons, so we don't have an issue balancing equations. The E naught for this one is 0.77 volts. Now, what happens is that since the green ones are not reacting with each other, this one is not reacting with this one. The iron ions, they start reacting with both of them. Starting with the first one, iron ions are going to react with, they're going to go and react with S2O8. And when they react with S2O8, S2O8 is the higher potential, so that starts gaining electrons, and Fe1 is the lower potential, so it starts losing electrons. And we can write the overall reaction that's going to happen, which is I'm going to add up the reactants. It's S2O8 2 minus. The other one is 2Fe2 plus. And I'm going to add up the products. The products are in both reactions. The first one, it's SO4 2 minus that's getting produced. And in the second one, it's 2Fe3 plus that's getting produced. So we're getting a reaction over here. And the E naught cell for this particular reaction, that's reduction potential minus oxidation potential, or the potential difference between the two is the 2.01 minus 0.77. That comes out to be What is that? Is that 1.24 volts? Can somebody confirm? Is this clear? That's 1.24 volts, right?
Yes, sir, 1.24.
Acha,
Sorry, sir, it's 0.24.
1.24,
Yeah,
0.77.
1.24, yeah. Okay.
Acha, then what happens is that the same, I mean, the same one, the same iron ions, they also go and they also react with, they also go and they react with iodine. So when they go and react with iodine, then what happens is that iron ions are the ones that are the higher potential. So they're the ones that gain electrons. And iodide ions are the lower potential. So they're the ones that are going to be losing electrons. So I'm going to construct this other reaction that happens. So it's Fe3 plus, that's one of the reactants, and in the other one it's I minus one, that's my reactant, so 2I minus one. And the products I'm getting is, so in the first one I'm getting 2Fe2 plus. ठीक है, if you look at the black arrow, this is the one that's gaining electrons, so it's 2Fe2 plus. And in the other one, it's iodine. So that's my second reaction. So that's, and the E naught cell for this is 0.77 minus 0.54. So what is that? That's going to be 0.23 volts. ठीक है? Is this clear?
Yes, sir.
Yes, sir.
So you got, that's one reaction. Iron ions reacting with S2 and that's your second reaction. ठीक है? Because the two electrodes were not reacting with each other because they were both negative ions. They were not reacting, so they ended up reacting with iron ions, both of them. Now, if you look at these two reactions, then it's the same reaction that we did over here. I mean, the reaction that we mentioned over here, having this E naught cell, which was very, very positive. This is exactly the same reaction because the S2 gets converted to SO4 2 minus, and your I minus 1 that gets converted into iodine. So it's kind of the same reaction, exactly same reaction. I minus 1 getting converted to iodine, so that is exactly what's happening. And what are your iron ions doing? They're not doing anything. It was Fe3 plus, which got converted into Fe2 plus, that got converted into Fe3 plus. And then in the next step, the same Fe3 plus got converted back into Fe2 plus. So the iron ions, they kind of remained completely unchanged. They did not do anything. So the Fe3 plus or Fe2 plus ions, they remain unchanged. So you got step number 1 and you got step number 2. The whole reaction got divided into 2 steps. And this reaction is very fast. You get the 2 steps are very fast. Can anyone tell me why the 2 steps are very fast? Yeah, anyone any idea? Like the previous reaction, Afan, कोई idea? Akshita, Amna, any idea?
Where catalyst is being used, iron is being used as a catalyst.
हाँ, लेकिन but why is this reaction fast? Why was that reaction slow? Because both ions were negatively charged, right? So like charges repel, so it was very hard to do that reaction.
These are positively charged, like oppositely charged. That's why.
ठीक है, so now what happens is both ions are oppositely charged ions. So you don't have to give them energy. They'll attract each other, they'll interact with each other, they'll react. So oppositely charged ions, they attract. And what that does is it lowers the activation energy. ठीक है? Is this clear?
Yes, sir.
Can you go up for a second, please?
Okay. So बाकियों clear? Akshita, is this clear? Maheen, Amna, Zohair, is
Yes,
this
sir.
okay?
Yes, sir.
But remember this example. You have to memorize. I mean, not memorize, but you have to remember this example. I mean, the equations better to memorize this specific example. Uh, like at least this part they'll give you if they give you a question on that. But you don't need to know how it's going to work. Okay, so that's one example of a homogeneous catalyst and how it's going to work. Now the next one is we're going to move on. Okay, so that's it. That's homogeneous catalyst. That's just one example. And if they ever ask you about some other particular reaction, what you need to understand is that if two electrodes are not reacting, then you can introduce a middle electrode which has a potential that's lower than the first one and higher than the second one. Then, but it's not necessary that that will act as a catalyst, because for it to act as a catalyst, uh, there has to be some reason why the reaction is faster compared to the original reaction. Uh, but you can break a reaction into steps. If two electrodes, they don't tend to react, you can introduce a third electrode, which has the in-between potential. So when the first one reacts with that, it gains electrons. When the lower one reacts with it, it's the lower one, so it loses electrons, and you get your products anyways. So we're now going to start talking about Hanji.
Mm, So for the electrode potentials like 1.25 and 0.23, so why we calculated that? Like it's not necessary, right? We don't need to
No, I'm
calculate
just
them in
saying
the
that it's
paper.
a I'm just saying that it's a positive potential. So that means the reaction is feasible.
Oh, okay, but they won't ask us to, calculate this in the paper.
No, they can ask you to calculate the E naught cell
Okay,
for a
okay, sir.
particular reaction. So now moving on. The next thing is that we've got now we're going to start studying rate of reaction, A2 rate of reaction. So first thing is we need to understand what do we mean by the term rate. So rate is basically change that's happening with respect to time. Any change that happens in a particular time. If the change happens quickly, so it's delta change. So if the change happens quickly, and this change could be anything, it could be a measurable change, it could be a visual change that's happening. So it could be a change in color, it could be a change in mass, it could be a change in volume of gas, it could be a change in concentration, it could be anything that's changing. It could be uh, a change in pH. So any change with respect to time. So one thing, remember, obviously you know how to measure the pH. You've got pH meters. You've got, I mean, pH meter is the most accurate one. Volume of gas, you know how to measure that. Mass, you can measure using a weighing balance. Concentration, you can titrate and figure out how the concentration is changing, right? Color, remember, is measured. It can be measured. You have values. It is measured using a colorimeter. And the colorimeter measures absorbance at a particular wavelength. Okay, let me. So remember color, all the other stuff you probably know all of how to measure that. So colorimeter is gives you absorbance at a specific wavelength. For example, if copper sulfate is getting formed, copper sulfate is blue. So it's going to give you values like how much copper sulfate or what's the intensity of the blue color that's getting formed. The more copper sulfate that gets formed, the higher the concentration of that particular substance. So absorbance is basically proportional to the concentration of the colored substance. Is that clear?
Yes, sir.
Yes, sir.
Okay. The rest you already know how to measure the volume of gas, concentration, pH, etc. You know that. Now, there are a couple of ways. Rate is change in concentration with this. Rate is change with respect to time. Technically, if you want to define something mathematically, it's also rate is. I mean, normally it's used. I mean, the most popular one, the most popular change, that is rate is change in concentration with respect to time. That is what you'll most often see. I said then there are many ways of finding rate. There are basically two broad ways of how to experimentally figure out rate of reaction. So if I have a reaction, like, although I'm going to test this one. So if I have a reaction, Mg reacting with HCl, and it's going to form MgCl2, which is a soluble solid, and it's going to give off H2 gas. So Mg is a solid, HCl is aqueous, MgCl2 is also aqueous, and H2 is a gas. Now, for this particular example, can you tell me what change should I measure with respect to time?
For gas, hydrogen gas for the reduction.
Okay, so it could be so the change I can try and measure, that's the volume of gas, right? Or what else can happen?
A decrease in mass of magnesium.
Because I can measure the mass of Mg. So what I can do is after every specific time intervals, I can take out Mg and measure its mass and see how much the mass changes. So I can plot a graph with that. The other thing is what else? I can if which one?
Dilute HCl.
Is it pH?
Yeah, you
pH
can
value.
you can use concentration of HCl. You can for that you would have to take out samples. I mean, there are two ways of doing that. How do you measure the concentration of HCl? You can measure pH. The pH basically kind of tells you the concentration of H plus one ions in the solution. So if the HCl is getting used up, the H plus one will start going down. The other thing that you can do is you can take out small samples at specific time intervals and titrate those samples to figure out the concentration of HCl, right? I said then there are other weird ways where I can figure out the rate of reaction. I can start measuring the bubbles of H2 gas getting formed. At the start, there would be a lot of bubbles formed. But bubbles of H2 gas would be like really hard to count. Um, I mean, I can take a picture every 5 seconds and count how many bubbles are there, but it's like kind of impossible to count how many. But there are many ways of finding or plotting or finding change. Now you've got two things. What you can do is you can plot a graph. And that graph on one axis there's going to be change, on the other axis you've got time. So the mass of Mg, if I plot the mass of Mg, that's a decreasing change. So I guess in the reaction, the mass of Mg will decrease very quickly. And then maybe if the HCl gets used up, it will stop decreasing, right? So the reaction stops. So let's say this is the mass of Mg. Same would be for the concentration of HCl. You would have a similar graph. Not exactly the same, but similar. Uh, if I plot the volume of gas, then for volume of gas, it's going to go up. But eventually it will slow down and the reaction is going to it's going to stop. So I've plotted graphs at regular time intervals. I've measured the change and I've plotted the value for that change with respect to time. Uh, so now tell me, what property of this graph is the rate of reaction?
So gradient.
ठीक है, remember the gradient is the rate. So the gradient of the curve is your rate. Now remember, you have increasing changes, you've got decreasing changes. So gradient could be negative. So gradient is negative if it's a decreasing change, like the mass of mg. As similarly, your gradient could be, it could also be, it could be positive as well. If it's an increasing change like the volume of, so it could be an increasing change as well. So it doesn't really matter because we're not interested in the, so you could have a gradient that's going up. And similarly, you could have a gradient that's going down. So for example, if I want to measure the gradient at this point, then it's going to look like this. That's my gradient. So remember, it doesn't matter. The minus and positive sign, ignore the minus and positive signs. So we're just interested in the actual value of the gradient, not the direction of the gradient. Okay, so only focus on the modulus of the gradient, which is, so we're just going to ignore the minus and plus sign. We don't care about the minus and plus sign. So you've got the gradient and that's your rate. Now, normally what happens is the graph is going to look like this, that it's, so the reactions are going to be faster in the beginning and they're going to be slower at the end, and then they'll eventually stop. So reactions are normally faster. So that means the gradient is going to be, it's going to be steeper. And why are they faster at the start?
Because there are less products.
Because the more reactants.
Acha.
So you have more frequent collisions, right? And eventually the reactants get used up. So the reactants eventually get used up. Acha, but remember, not all reactions are going to follow the same behavior. A lot of reactions are not fast in the beginning. They actually speed up in the middle. Eventually, they will slow down because eventually the reactants, you'll run out of reactants and the reaction is going to stop. So keep this in mind as well. Not all reactions.
आप क्या ऊपर जा सकते हैं प्लीज?
ठीक है, एक सेकंड.
Okay, thanks.
हो गया?
Yes, I just need to see something.
चल ठीक है. अच्छा, not all reactions are fast at the beginning. Some reactions are not fast in the beginning. One example is that aluminium with acid, ठीक है, it's not fast. The example, aluminium plus, let's say HCl. What do you get? You get AlCl3. And you get H2 gas. 3, 6, 2. Achha, can somebody tell me why is aluminium with HCl not fast in the beginning?
Is it because oxidation? No. like
Awesome.
a
It's
layer formed on top
ठीक है. So it's
to
got a
prevent
it's
further
yeah, it's
reaction.
yeah. So it takes time for the oxide layer to dissolve in the acid. So what happens in this case is that the graph would kind of look like this. It's like if I'm measuring the, let's say, the mass of Al, right? As a lot of things that I'm going to teach in this topic are going to be related to P5 as well. They'll probably not show up in P4, but I mean most of the stuff that I'm teaching right now that's more targeted towards P5. Because there's a lot of experiment. Anything that's related to experiments, that's probably going to show up in P5. So the graph would kind of look like this, that the mass of Al would initially not change, then all of a sudden it will speed up. And then it will start slowing down, and then the reaction would stop, right? So the graph would kind of look like this. No mass changing in the beginning, then all of a sudden it speeds up, and then it slows down again because you run out of reactants. Then there are some other reactions which are also not very fast in the beginning. These are known as autocatalytic reactions. Now, the thing with these reactions is that the product is the catalyst in the reaction. So the reaction happens and the product gets formed. And as soon as the product gets formed, the product catalyzes the reaction. So the reaction starts speeding up. So for example, if I have X plus Y reacting and it's forming Y and Z, right? Not Y and Z, but let me put W over here. X and W reacting, forming Y and Z. Now what happens is that, let's say Y is the catalyst. So initially the reaction would be slow. And as soon as Y gets formed, the reaction starts speeding up. So the graph would kind of look like this. Whatever the graph is, I haven't written down a reaction, but there would be very few reactions where they're not going to be fast in the beginning, but the product is going to start acting as a catalyst. Is this clear?
Yes, sir.
Yes, sir.
ठीक है. So now, so this is one way. ठीक है? You're going to plot this graph and you're going to figure out the rate of reaction by drawing a gradient. Gradient is basically your rate. And let me highlight that. So the gradient of the curve is basically your rate of reaction. And also a few things. Which rate would you be more interested in? Like, do you want the rate of reaction? Like, if you want to analyze the reaction itself has many different rates. It's fast in the beginning, slows down, then becomes zero, right? So whenever you try to measure the rate of the reaction, it's always the initial rate that is always measured. You always measure the rate right at the beginning at t is equal to zero. You're gonna put 2 points over there and you're gonna make a gradient. So always compare. I mean, they can ask you rate of reaction at any time, but for comparison purposes, normally what happens is always compare initial rates. We don't care about the rate of reaction after 5 seconds or after 1 hour. We care about the reaction right at the beginning. What is the speed of the reaction right at the start for a fair comparison? Okay, is this clear?
Yes, sir.
Yes, sir.
Okay, it's going to be pointless to compare the rate of reaction at after 1 hour or even after 5 minutes. Some reactions they are over in 5 minutes. So always at t is equal to 0 when you plot this graph. So now there's a second method of measuring the rate of reaction. In that case, you don't need to draw a graph. So the second method of, one is this gradient thing. अच्छा अब जो second one है ना that's so the second method for finding rate, and this is without graphs. So this method kind of measures the initial rate directly without drawing any graph, without drawing any gradients. Now what you do in this method is, remember the rate was what? It was change in concentration, any change with respect to time. That was what rate was. So what you can do is you can instead of following the change like the way we were doing over here, we were plotting the change with respect to time. So what we can do is we can keep the change fixed. Whatever the change is, we will fix it. This is how you measure and you instead just measure time. You keep the change fixed. Okay, so for example, if there's a 100-meter sprint in the Olympics, no one is measuring meters per second for each runner. They're not doing that. They're not plotting the graph and they're not drawing gradients, right? No one does that. This method that I just taught, that's highly inconvenient. No one does that. Okay, if there's a car race, no one is plotting at what distance the car is at a particular time and then they start drawing gradients, right? What they do is they just fix the change. The change is 100 meters, right? And they just look at the time. That's it. So by just looking at the time, as long as the change is fixed, if it's the same change. For example, I can treat reactions as a 100-meter sprint. And the final point of the sprint is, let's say the time taken for 5 cm cube or 10 cm cube of H2 gas to be produced. So I do a reaction and I just look at the time that is required for 5 cm cube of H2 gas to be produced. So since my change is fixed, my rate is basically inversely proportional to time. Whoever has the slowest time, that is the fastest reaction. Right? Is this clear?
Yes, sir.
Because this is a lot easier. You just start a stopwatch. You've got a syringe. You start the reaction and you just stop the stopwatch when 5 cm cube of H2 gas gets produced in this reaction, the one that we did over here. Or there could be other changes. For example, if I have a 2-gram piece of magnesium, I start the stopwatch and I see how quickly the 2-gram piece of magnesium dissolves, and I stop immediately when it dissolves. Uh, and I do several reactions, right? So I don't need to do any of the graphs. I don't need to draw gradients. I can just simply figure out rate by looking at the time as long as the change is exactly fixed. Because then it's not going to be a fair comparison. If one reaction, it has 5 cm cube of H2 gas getting produced, in the other reaction, you're looking for 50 cm cube of H2 gas, then that's not a comparison. Okay? For a fair comparison, the change has to be exactly the same. Okay, is this clear?
Yes, sir.
So you can directly measure rate. Rate is just 1/time. No further calculation, graphs, gradients, etc. Nothing needed. Uh, but this graph has its value. The reason it has its value is because it shows how the rate of reaction varies with respect to time. So it kind of tells you, like even 100-meter sprints, right? When the runners analyze it, they make graphs out of their sprints because they want to know exactly how whether the reaction was really fast in the beginning, how fast was it after like 30 seconds, what happens after 15 minutes. So this graph has its own values, while this one only tells you the initial rate. So this one is only good for measuring initial rate. Okay, is this clear?
Yes, sir.
But like in this, we could measure like data as well, right? Because maybe initial is like around 5 centimeter cube, but then we can also see the rate at 10 centimeter cube as well.
But that will still be counted as an issue. You're starting at zero, right? I mean, what is the first point? You're starting at zero, right?
Yeah.
So the only thing
Wait, so
you're like
what
for
differentiate the, yeah,
well, for example, H2
sorry.
gas gets produced in this way, right? Okay, this is too steep. Just 1 second. For example, H2 gas gets produced in this way, right? So the 5 cm cube mark could be over here, right? 5 cm cube mark. And this is the time taken. But it's basically you're doing the time taken from zero, right? If you
Yeah.
move to 10 cm cube, then it would kind of be more inaccurate, but it's still the initial rate because then you'll be measuring the time that is required for. But it's still your starting point is zero and you're ending at 10 cm cube, right? You're measuring how quickly that happens, right? So the further you go,
Um,
the more inaccurate you're going to be.
okay. So the reference of initial rate is just that like you're measuring time from 0 seconds,
Yeah.
but then that could be initial rate at when there's no more gas, when there's no more rate of reaction as well, like because
Nee,
we're
at
still measuring time from 0 seconds. Like when it goes flat, we're
yeah.
still looking at the time
That's
from
what I'm
zero
saying
seconds.
then. Like if you're looking for let's say maybe if you're looking for if you go for a 50 cm cube mark, right? So maybe that never gets formed. So your time would just keep on going on. So the point is this method only works if you're looking for the initial like what happens right at the beginning. It only makes sense if you're looking at the right at the start of the reaction. Do you get my point? Because
Yes, sir.
this method only works for right at the beginning of the reaction because then it kind of becomes inaccurate. Measuring 20 cm cube maybe it never forms 20 cm cube of gas. So the method will not probably work for larger volumes or larger quantities. So you're just going to look for the initial change. That's it. Is this clear?
Yes.
Yes.
ठीक है. So ठीक है, let's continue with the orders of reactions then. We will do that tomorrow then. ठीक है?
Okay, sir. Allah Hafiz.
Allah
चलो.
Hafiz.
Okay, take care.
Thank you, sir.
Love this.